Okay, so this is just a short video on isomerism. There's three types of isomers that you need to know for level 3, two of which you learned last year. So if I just start off with a general definition for an isomer. So an iso, the prefix iso means the same. So an isomer is they're compounds with the same molecular formulae. So they all have the same molecular formula, but different arrangement of the atoms. Okay. So an isomer is a compound with the same molecular formula but different arrangements of the atoms. The molecular formula will always be the same. So the molecular formulae of all isomers of a compound, so a particular compound, will always be the same, and that's what makes them isomers. Be the same. So the next thing to talk about are the three types of isomerism that you guys need to know. The first type is structural isomerism, also referred to as constitutional. So structural isomerism or constitutional isomerism. Okay, this is where you have the same molecular formula, which is the standard definition for all isomers, but that the bonding differs from one to the next. So if I just give you the molecular formula C4H8, now there's no real systematic way to figure out all the isomers for a particular molecular formula. You just have to draw them out and just check each time that you have 4 carbons and 8 hydrogens in this case. So we start off with the simplest one, which is to simply just put them in a long carbon chain. So if we put 4 carbons in a chain, straight chain, and then if we start adding hydrogens, we put 3 hydrogens here, and we have 2 on the next carbon. Okay, on this carbon we have another 2 hydrogens. So you can see we have 1, 2, 3, 4, 5, 6, 7, and that leaves us with only 1 hydrogen left. So we're going to remove one of these hydrogens, and that means we must have a double bond in this compound. So we put a double bond here, and then the 2 hydrogens go on here. So that first compound is but-1-ene. So it's a 4 carbon chain, the double bond is in position 1, and you've used up your 4 carbons and your 8 hydrogens. So that's one legitimate isomer. Now the next thing we're going to do is we're just going to simply shift the double bond into the middle position. Then you'll still have the same number of hydrogens. So you'll have your 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, your 4 carbons and the double bonds in a different position. So this is definitely a different arrangement of the bonding than in the first one. This is in fact but-2-ene, which is another isomer. If you continue and move that double bond onto that position, well then that is the exact same as this molecule up here. It's just being rotated 180 degrees in the plane of the page. So just be aware of that. So those two are the same. So but-1-ene and but-2-ene, that's 2 isomers, and there's a third isomer you can draw for this compound, which involves 2 carbons that are double bonded together, but in this case we add 2 methyl groups as side chains, and that carbon has 4 bonds. You got 6 hydrogens there, and then you got your other 2 here. So that also follows the molecular formula of C4H8, and this one is 2 methyl 1-ene, 2-methyl-prop-1-ene. So that's just a little trip down memory lane as regards structural isomerism, which you learned in level 2. And as I say, there's no systematic way to approach doing them. You just need to make sure that you count up your number of atoms in each case and make sure that they match up to get the molecular formula, and just check that you haven't drawn an isomer which just happens to be the same as another one which is rotated 180 degrees. Second type of isomerism we covered last year was known as geometric isomerism. geometric isomerism, also known as stereoisomerism. Okay, so geometric or stereoisomerism. Now, the key to understanding these was to look for some telltale signals of a molecule which could have geometric isomerism. And the first one was that you had a carbon-carbon double bond. And the second point to look for was that each carbon had two different groups attached. So double bonded carbons and two different groups attached. So if we take a look at one example, we refer back to the but-2-ene molecule we had here. Well, the but-2-ene molecule has to have two different side chains on it. So we're going to take the following. So but-2-ene is going to have a methyl group on one of the carbons, and then also a methyl group here. But this is okay because each of the carbons individually have two different groups. So I'll just say that again. So the criteria was that we had to have a carbon-carbon double bond. So there it is there. So we've fulfilled that criterion. And then each carbon involved in the double bond must have two different groups attached. So I'll highlight that for you in green. So this is carbon number 1 if we want to number it, and this is carbon number 2 in this case. Carbon number 1 has these two groups attached, two different groups, methyl and hydrogen, and carbon number 2 has two different groups attached. Okay, so then the other thing you would have learned for this was that there are two possible geometric isomers. You can have the cis isomer, so this would be cis but-2-ene, or you can have the trans situation where the side groups are arranged on opposite sides to each other. So the trans but-2-ene, this is written in italics by the way, the trans but-2-ene isomer would look like this. It's quite a straightforward question if you get it in an exam. It's amazing how many students don't answer it properly simply because they don't use the key terms. So on opposite sides, so if we look at the methyl groups there, just as an example, they're on opposite sides of the double bond, and so too are the hydrogens. So this would be the trans but-2-ene geometric isomer. So cis and trans. The main thing with the cis and trans isomerism is the double bond prevents rotation, because if you actually make those up with mods, you can't rotate that without breaking the plastic. So there's no rotation around a double bond, whereas in the single bonded compounds you can have rotation around a single bond quite easily. So no opportunity for geometric isomerism unless you have a double bond. Okay, now the third and newest type of isomerism is optical isomerism. So we'll use a new page for this. So number 3, optical isomerism. Now this typically is the only type of isomerism that you will get assessed on in level 3, but there's no reason why they can't throw a question in on structural or geometric. With optical isomerism, there's some key things to note here. The first thing is that you look for a carbon center with 4 different groups attached. 4 different groups attached. Okay. And the easiest way to illustrate this is to just pick a compound. So if we do the compound, and we did this in lesson today, 2-hydroxypropanoic acid. 2-hydroxypropanoic acid. And some students pointed out the fact that I hadn't referred to hydroxy before as a prefix. The prefix hydroxy is used if you have an OH group which is present as a side group. And the reason the hydroxy is a side group in this case is because the suffix, which always gives you the family name, is for a carboxylic acid. So what we have here is a 3-carbon carboxylic acid which has an OH group at position 2. So if we draw that out, hopefully we'll be able to illustrate where the chiral carbon is. So for 2-hydroxypropanoic acid, we do a 3-carbon chain. We put the standard carboxylic acid group on the end, always on the end, and then the hydroxy group, or OH group in this case, is going on to carbon number 2. CH3 there, and a hydrogen on there. Now, we said that in order to have optical isomerism possible, we need to have a carbon center with 4 different groups attached. So I'll highlight that here. Our carbon center is this one. It has the OH group, it has a methyl group, it has a hydrogen, and then it has the carboxylic acid functional group. So that's your chiral carbon, is what it's referred to as. Chiral, C-H-I-R-A-L, chiral carbon, or center sometimes it's referred to as. All right, the next thing we want to talk about with optical isomerism is that you can have two isomers for an optically active compound, or they're referred to as enantiomers, 2 enantiomers. So just get used to that key term. Isomers or enantiomers, essentially the same thing, except this is specific to optical isomerism. Okay, the next thing we want to talk about with optical isomerism is that they are non-superimposable. This is another key idea, non-superimposable. And we just introduced this idea in lesson. We said if you took your left hand and just traced around it, okay, and then if you took your right hand and tried to put it on top of your left hand, let's try and draw this properly. Okay, so if you try to put your right hand directly on top of your left hand, you'd form a shape roughly like this. You'd have one thumb on one side and one thumb on the other side. So the two shapes do not perfectly superimpose, and that's what non-superimposable means. Now if we compare that to the two enantiomers of 2-hydroxypropanoic acid, so I'll quickly redraw the molecule here. I'm going to use dashes and wedges just to represent the molecule. So if we start off with our chiral carbon, in the plane of the page, we're just going to put in our OH group. Okay. Coming also in the plane of the page, the carboxylic acid group can be condensed to COOH. Then at a slight offset, you have your wedge, which means coming out of the page, and that has to be filled in. So that's a filled in wedge. In this case, we have just a hydrogen coming off that. And then going into the back of the page, we have our dash. We want to illustrate that using the wedge, dashed wedge rather, and that's going to be a methyl group, CH3. So that represents the 2-hydroxypropanoic acid enantiomer that we drew initially. Okay, so if that represents, if the methyl group here represents the thumb, that can represent the left-handed model. If we were to put a mirror beside this compound, we would be able to illustrate the enantiomeric pair of this compound. So we'll just still draw down our chiral carbon. Our OH group is easy, it's still at the top. The COOH group, though, is coming out this way now, whereas the methyl group is now round the back here, and the H group, or hydrogen, that's easy enough, we can just put it right there. So in this case, you can see that if this molecule represented your right hand and this molecule represented your left hand, then those two molecules are not superimposable, and that's what this concept means here. Okay, the other thing now we need to talk about, and this is what is included on exam questions, is the next thing they would say is how could you distinguish between these two enantiomers experimentally. So now we're going to talk about the optical activity of optical isomers. The optical activity of optical isomers. All right, so it's quite a simple concept. I'm just going to draw a piece of equipment to try and illustrate what happens. But if you take two different enantiomers, we'll just take glucose as an example. C6H12O6, classic science compound everybody knows from the equation for respiration. There are two forms that you can find for glucose, and a good technician will label the container as either D-glucose or plus glucose. or you can also use or glucose. In all cases, they mean that this isomer rotates plain polarized light um, to the right hand side or in a clockwise direction. Alright, and then the opposite of the D isomer is the L glucose, also referred to as negative glucose, also referred to as S glucose. And this isomer rotates plain polarized light to the left-hand side or anti-clockwise. Alright, to just talk about the piece of equipment which does this, so if I do a little rough diagram here of what we mean by plain polarized light. If you take a light bulb, that's a light bulb, light will come from all directions directly from a light bulb, and what you want to do is you want to take those rays which are in all plane of the 3 dimensions, all planes of the 3 dimension, and you want to use a lens to trap one section of the light in one plane. So what you end up having is you get light coming in just one plane. Then you pass it through your sample tube, and as that light passes through the sample tube, if it begins to rotate to the right, then you say that this is the D glucose sample, whereas if it rotates it anti-clockwise to the left, then it would be the L glucose sample. Other thing I mentioned in class was a concept known as a Racemic mixture. A Racemic mixture is an even mixture of 2 different isomers, so this would be an even mixture of the L and D glucose in your sample tube, in which case you would have no activity or no rotation of plain polarized light. Okay, so that's what a Racemic mixture is. The only other thing that we talked about then in lesson was just to give some real-life context for this concept of discerning if a compound is optically active, and it's very, very important, especially in the production of anything which is for human consumption. I'll just read about the thalidomide story because it's quite well known. I'll just read this out and we can finish the video on this. So in 1956, a new drug was released on the market. It was a mild sedative useful for people having trouble sleeping or who were anxious or depressed. It was also offered to pregnant women troubled by morning sickness. Thalidomide was effective in all these areas and seemed to have virtually no side effects. Sales soared. Meanwhile, in maternity homes around Europe, the birth of deformed babies was also rising. There have always been some babies born with defects, but in the late 1950s, far more seem to have been born than usual, many with the same types of defects such as extremely short arms or legs completely missing. After 5 years of research, it was finally realized After 5 years of research, it was finally realized that what these babies had in common was mothers who had taken thalidomide in early pregnancy. Thalidomide is optically active. One enantiomer has the desirable sedative properties, while the other acts as a teratogen. It causes damage to a growing fetus. Up until this time, it had not occurred to scientists that a drug that was safe for general use may not be safe for pregnant women. After the thalidomide tragedy, the testing procedures on new drugs were changed. It is now much harder to get a new drug approved for use.